Welcome to Everything Distributed. Today, we are going to talk about approximate consensus again because I realized that proof actually is non-trivial, and I want to talk a little bit about how we usually approach this kind of proof. So just to remind you, what's approximate consensus? We assume that we have at least two F plus one nodes, and consensus property is a termination, agreement, and validity. And termination and validity actually is pretty simple because we only deal with cross failures, and agreement is the difficult part. Okay. And here again is a review. What kind of approximate consensus algorithm that we are dealing with? We have n nodes, and then they proceed in a synchronous run. Initialization is a yi. Each node has a state yi, and then it's given input xi, and then I have a run r equal to 1. Start with run, asynchronous run with index 1. And I just exchange message with each other. And then I need to wait until I receive m-f message. And then the fourth step is that I'm going to update my new state, yi, as the average of all the message that I receive. And I proceed to the next run. Okay. So very simple algorithm. And the key thing to remember is this m-f thing. Later on, we will use this to prove the convergence or to prove the agreement. And this m-f is very useful for other kind of distributed system, and especially the quorum-based one. And we will see this thing again and again. So termination, as I said, is pretty easy. You can have a fixed number of rounds that you want to execute, and then we have a validity because we are doing average. So it's pretty obvious that the outputs will must be inside the convex hull. Okay. And then last time I mentioned that, okay, in order to prove the approximate agreement, meaning that the output will be the state yi and yj will be closer and closer as t increases. So then we need to have some formalism to help us to proceed with the proof. And then we start with RIT, meaning all the values, all the message received at I in run T. And then we also have RJT, and then you use based on RIT to update your new state, which is YIT and YJT. And then the key thing here, usually we think that RIT is some kind of quorum, meaning that I receive a value from a set of nodes. And also we can define similarly for RJT. And the key claim we want to prove is that this YIT intersect with IJT, this set is non-empty. And then the two observations we want to use is that n strictly greater than 2f, and the size of RIT and the size of RJT is exactly m-f. Okay. And then one mistake I usually find out for a new student is that you directly jump to the conclusion you want to play with these two number m-f and then n greater than n strictly greater than 2f, but you don't really have intuition. So usually I recommend you to start with the simplest example. At first, if I start with f equal to 0, that means that you are going to wait for everything, so that's trivial. There's nothing to show. Okay. So what is the smallest examples that you can use, which is f equal to 1 and n is equal to 2f plus 1, so you have n equal to 3. And then without loss of generality, you can assume that you have 3 nodes, and each of them has a state 1, and then the second one has state 2, and the third one has state 3. Now you just kind of do counting and then see that what is a reasonable Ri and what's a reasonable Rj. Okay, so for this, now let's do something. So for example, suppose I receive only 2 messages because I'm going to wait for 2 messages, then I will get 1, 2. Then for the other person, suppose for you, if you get 1, 2, then that's good. We have the same thing. There's nothing we can prove, nothing we need to prove. So now the question is that is it possible to find another set of nodes such that you receive the value from, and then there's no intersection with me? And then you can say, oh, maybe 1, 2, I can try 1, 3, or I try 2, 3. And no matter how I draw, there will always be one elements that are common for us. So at this point, if you are not convinced, you should try some larger example. So example like f equal to 1, n equal to 4, or like f equal to 2, n equal to 5, like so on and so forth. Then you will find out that, okay, this claim seems very, very obvious. But then how do I approach the formal proof, okay? But like, please always start with example. Then this will give you some insight and some intuition, okay? And then let's go to the next one. And then the other way, and then the other thing I observe is that one common mistake, oh, sorry for the typo, that there's only one mistake, is that you got confused with this notion f. So like when you see f equal to 1, you simply assume that, okay, like one of the nodes already crushed, so I'm only left with like two possible value, 1 and 2, so that everybody must receive 1 and 2. And then that trivially proves the claim. And this is not true, okay? So remember, what is the meaning of f? The meaning of f is the upper bound on the number of 40 nodes. So it is very possible that in the execution and this exact moment, nobody failed, just as some nodes that slow. So in that case, it's still possible that, okay, maybe 3 is slow to me, so I get 1, 2. But like 1 is slow to you, so you get 2, 3, okay? But that doesn't mean that like one of the node already crushed. And then, so if you start with say that, okay, I already have some 40 node, I can just include that node, then this is a false direction, okay? So we want to have a general argument. Of course, if you are trying to do some example, you can say, okay, one guy has already died, that's pretty good, then that's an easy case. But you should be able, or you want to be able to identify that this argument is not general enough, okay? So good. Then let's go to the next slide. So the next slide, the other thing that you can see is that, okay, now I know that it works for f equal to 1 and n equal to 3. What if I reduce n by 1? Then in this case, remember, I only need to wait for n minus f message, meaning I only need to wait for one message. So in this case, it's possible that I get 1 and you get 2. Then there is no intersection. There's no common value between you and me, okay? And this should give you a hint on how to prove the claim. Then now let's do the proof together. So based on all the observation and the examples we have proved, then we should be able to do this, the kind of counting-based argument. And then the way to do this is to start with a proof contradiction. Let's say proof by contradiction. So what we want to do is that we start with a false assumption, meaning that start with the negation of the thing we want to prove. So meaning that Ri and Rj share no common value, okay? And then because of this argument, what we can know is that this actually implies that the union of Ri and Rj, what's the size? The size of this union is that 2 is equal to 2 times the size of Ri. Sorry, it should be Ri plus Rj, because that they contain only the unique values between the two sets. Then this thing that said that should be 2 times and minus f. Okay. Then once you have this first observation, then if at this step you directly want to use n greater than 2f, n strictly greater than 2f thin, then you will get that very confused because you just plug in and then you say, oh, okay, I know the size of this, so I know that this is at least 2 times f, because 2f minus f is equal to 2 times f, but this doesn't give you anything. Okay, so this is not the correct direction, then you got stuck. But it's okay if you get stuck. Like for this kind of proof, it's very common that you got stuck, but like we just need to figure out that, okay, this is not a right way, let's try the other approach, okay? And then as I said, for distributed computing, even though we argue for the very abstract level, but like if you are able to draw some figure to help you, actually it's not so bad, okay? So now let's think again, what is the meaning of Ri and what is the meaning of Rj? So forget about 2 times n minus f for now. Let's just say that, okay, this is Ri, meaning that all the nodes that have sent a message to I and I has received from them, okay? And then we also have Rj, meaning that all the nodes that have sent a message to Rj, and then Rj has received those and used those to update its value, the state value. And remember, we start with the assumption that these two sets, they share no common value, so we have two sets that we know. And now the question is that, how do we bound the size of these two circles? Okay, and then this is a very common trick that we can use to derive contradiction. Okay, and then if you think about this Ri, who can send a message to Ri, and then who can send a message to J, and then you will realize that actually this thing is bounded by n, because all the possible messages are from individual nodes. There's nothing else. Okay, so just by this figure, you will be able to reason that Ri union Rj actually is bounded by n. N is greater than or equal to this thing. Okay, so that's a very second important observation, and just because of the figure. And now we can start plugging the number. So n is greater than or equal to Rj, and then from the thing up above here, we also know that n is greater than or equal to 2 times Im minus f, and then we can just shuffle things around. Then we have we have 2f greater than or equal to n. So at this step, what do we derive? We have derived the contradiction, right? So if you remember, we start with the assumption that n is strictly greater than 2f. But now, if we have the false assumption, we say that no, actually n is upper bounded by 2f, and then that's how we show that, okay, these two are contradicting with each other, so we successfully complete the proof by showing the contradiction. Therefore, this assumption is not correct. That means that Ri and Rj must share a common value, and then this complete the proof of the claim. Okay, so that's good. Then, oh, actually, let me erase the drawing. Good. Now we have the key claim. So the next exercise is showing this approximate agreement, or sometimes we call convergence. is that we define a yit and we define a yjt, and they must approach to 0 as t increases. And then this rely on the key claim of RIT and RJT share a common value. And then there's a simplification I want to make for you. So if you remember, our algorithm actually take the average of RIT, but right now for YIT, I just take the max of RIT plus the minimum of RIT and divide over 2. That's your new state. And then anything in the middle, I don't really care. Okay? So now let's look at how to prove this. And then for this kind of proof, remember, we want to bound the difference between yi and yj. And then usually it's a much easier to start with a simplification. So without also generality, let's assume that yi is greater than yj, greater than or equal to. Okay, so now what's your goal? Your goal is like bound yi minus yj. Let me increase this. So that's your goal. Then remember what's yi. Yi is equal to max of Ri plus min of Ri. Then these two things, I'm going to average it. Okay. Then usually for this thing, right, we want to bound the yi minus yj. So intuition is that I want to find the upper bound for yi and lower bound for yj, because that will give me the maximum size of this, like the difference yi minus yj. Okay. And then in order to this, you will need some like formal intuition, formal notation. So now let me introduce like two things. The m is the max state value. Let's just say max state value in run t. And then the lowercase m is the minimum state in run t. So if you remember, we have an example of 1, 2, 3. So in that case, the capital M would be 3, and then the lowercase m would be 1. Okay. And then in this case, what would be the upper bound for yi? So think about it. In this case, it's like you will want to say, oh, okay, I can just like, okay, max Ri is upper bounded by capital M, and then minimum Ri is also bounded by capital M. But like this is actually not really helpful, because what this gives you would be that yi is equal to, so if I just plug in yi is equal to m plus m over 2 is equal to m, then this doesn't lead you to anywhere. So even though this is a good try, actually this is not enough. And then remember, we have the claim, and somehow we need to use that claim. Okay, so like Ri and Rj, they share a common value. So what we want to do is that we can introduce another name variable, c is equal to the common value in Ri and Rj. Now, this is good enough in order to complete a proof. And then I directly tell you this conclusion, because that the argument to lead to this conclusion actually is really, really simple. Okay, so yi can be upper bounded by m plus c over 2. And what you need to show is that obviously max Ri is upper bounded by m. Then you will want to convince yourself that this min Ri is also upper bounded by c. Okay. And then the next one is yj. Then what will be the lower bound for ij? So yj is actually greater than or equal to c plus m over 2. So the min rj it must be at least lowercase m. This thing, so like the thing you want to convince yourself is that max ri is greater than max rj is greater than c. Good. So once you get this step, you are almost done. Then now you just combine these two inequality together. Yi minus yj is greater than or equal to the difference of those two things. Okay. So now I just get a 1/2 out. Then I have m plus c minus c plus m. So what's this? The common value is cancelled out. And then it turns out that's all we need, okay? So what we get is m plus m over 2. So what does that mean? That means the difference between any two nodes yi and yj would shrink by half in one run. And then because this applies to every pair of node yi and node j, and then this is enough to show approximate agreement. And then for that, the final mile for the completed proof, I will leave that as an exercise for you. Okay. So that's about it. And let me clean the drawing. Good. So we have completed the proof for approximate agreement, and then we prove two things. The first one is the claim. We use this counting-based argument. So we draw the figure, we have two circles, and then those are bounded by n. Then you just move things around, then you can prove it. And then the next one is that we prove the bound on yi minus yj. And then for that, you will want to get an upper bound for one value and then the lower bound for the other value. And then the key is that to use this C thing, the common value inside. So later on you can cancel them out. Okay, so that's all for today. Thank you.